Today I'm going to give you a third lecture on microkernels, and after giving you an introduction to why microkernels are cool and what the fundamental mechanisms are that the Fiasco.OC microkernel provides you, I'm going to talk about more advanced components on top of it today. So I told you already that Fiasco basically provides the three fundamental mechanisms. One is tasks or edge spaces, which are used as containers for resources, such as memory management. Then we have threads, which are the units of execution, which communicate in order to provide a service to users. And we have IPC, or inter-process communication, as the fundamental mechanism to exchange data, to implement timeouts, and to map resources between resource containers. So now we have this little kernel with these shiny features, but what are we doing with that? And today I'm going to show you what we can do in order to build real systems using these mechanisms. And building such systems means that we want to use legacy libraries, such as a POSIX C library, because everyone who's programming in C is somehow expecting C libraries to be available. I'm going to give you an introduction on how to implement device drivers in user spaces on top of a Fiasco, which means we will have to have a look at how we access hardware resources, and we'll have a look at how we can reuse existing Linux device drivers instead of writing everything from scratch. And finally, in the end, I'm also going to talk about virtualization in terms of virtual machines on top of L4Re. So first of all, when we build a real system on top of a microkernel, what we'd like to have is some kind of reuse of existing legacy software. And the reason for that is that, for one, users want convenience. So if I'm using a new operating system and I can get my shiny favorite application, such as my web browser or my favorite email client, then I'm happy with it. Because people are used to working in certain lines of thinking, and if you give them their tools, then they're more happy with your software than if you make them learn everything from scratch. The other part is effort. When you build a new operating system, you have to think about a lot of things. And if you can leave out some stuff because you can reuse an existing C library instead of writing your own, then you're getting to your target faster. Because rewriting everything takes a lot of time, you make a lot of errors, it takes a cost in debugging. Whereas if you port or reuse existing software, then most of the time you're faster at your goal. However, as people learn from experience, is that maintaining ported software instead of writing your own sometimes also costs you. So it's not completely free, but in most cases it's easier to reuse existing software. So here are a couple of ways how you can do that. So suppose you have an existing library or an existing application which runs on your favorite Linux distribution or on Windows or whatever. What do? So the first way to do is you take the application source code and port it to your target operating system. So this means you have a look at all the source code in the application and see whenever it uses Linux memory allocation, you adapt it to use L4Re's way of allocating memory. And whenever it accesses a file, you adapt it to use L4Re style communication to a file server and so on. This has the advantage that in the end you'll end up with a pretty efficient application because it's directly using all the mechanisms provided by the underlying kernel and runtime environment. However, the effort of porting and maintaining the software is pretty high because you have to inspect all the source code and you have to understand what's going on in the application, you have to test a lot, so it's pretty hard to do. One layer higher, what we can do is we can take certain libraries which many applications use and only port those libraries, and by making those libraries available on L4Re, all applications that use these libraries pretty much run without modification. And this is what we do, for instance, with the POSIX C library, as well as with the standard C++ library. So we take those libraries and adapt them to run on L4Re, and The good part is, once we're done with that, which of course costs us effort again, then we can use any application that's using a C library and simply run it on L4Re unmodified. Again, one layer higher would be to kind of provide some emulated operating system environment, such as what Wine does for Windows. So what Wine does, it's basically providing you with an emulation library that makes applications think they're running on Windows, even though Wine maps all those Windows calls to underlying Linux calls. And this is some kind of a different from the library approach in that you're not linking your application against the library, but you're providing some kind of interface that wraps around your application. And if you take this to an extreme, you end up with virtual machines, which basically provide a complete abstraction of hardware, so that any arbitrary operating system thinks it's running on native hardware, and your virtual machine pretends to be a computer, basically. And I'm basically going to talk about the last 3 points today to give you examples on how we do that and how it works on L4Re. Let's start with our monolithic operating system picture we already saw a couple of times. So usually in a monolithic operating system we have user mode applications, and the user mode applications use some kind of system call interface provided by the operating system kernel to achieve whatever they want to achieve. If we move over to a microkernel system, we basically moved out a lot of functionality from the kernel and provide a communication mechanism so that applications may use each other's services. So we could have the application on the left, for instance, talking to a file system server in order to obtain access to a file. And the file system server in turn would then talk to a user level disk driver in order to access the hard disk, for instance. We may have another application which uses the file system server for file access and a network device driver directly sending Ethernet frames. On the other hand, we might have the application on the right, which uses a TCP IP stack, again implemented in user space, which in turn uses the network driver to send TCP IP packets. And applications may also use each other's services. The problem in such a system is that instead of using some kind of a generic system call interface, this becomes pretty complex because you have to keep in mind all the interactions between the applications. Everyone needs to be aware of which server is providing which service, how does the interface for this service look like, and decomposing a system is in general seen as pretty hard. Even though it gives you the most flexibility and gives you the best performance usually, it makes things hard. The first idea to solve this problem would be to provide some kind of a user-level Linux abstraction. Let's call it the Linux operating system personality, which would be some kind of a server that provides a Linux system call-like interface to applications, so that all applications would only need to talk to the server and use something similar to Linux system calls. And the server can then implement whatever a Linux kernel would do. So it could manage some kind of file descriptor and some abstraction for files, which it would then internally map to calls to the file system server. It would provide some kind of sockets, which it would map to calls to the TCP IP server, so that in the end the Linux OS personality is the only place that needs to have knowledge about the underlying microkernel-based system, and the application can basically use the same interface they use from Linux. While this sounds cool from an application developer's perspective, because you don't need to learn any new interfaces, you simply reuse your knowledge about Linux, it becomes pretty hard to implement such a personality. For one, because you need to come up with all the abstractions that applications might want to expect and map them to the microkernel services below, which is pretty hard. And on the other hand is, once you're done with this complex implementation effort, you still have the problem that this Linux OS personality becomes the bottleneck in the system, because all the other applications would communicate with it, and this basically means you're going to spend a lot of time executing here. You need to optimize this to become performant, and it's again hard to do. Actually, historically there was a huge effort done by IBM in the 1980s and 90s to implement an operating system providing different personalities. So that what they wanted was an operating system that was able to run Windows applications, Linux applications, as well as OS2 applications. And they wanted to solve this using this approach, basically. And in the end, what they did was they spent billions of dollars on the project, and the project failed. And one of the reasons is that basically the whole complexity was unmanageable at this time. And so maybe OS personnel fields aren't that a good idea as well. So here's what L4Re does. Fundamentally, in Linux, many applications simply rely on a C library being available. And L4Re provides this. So you get a C library which you can link your L4Re applications against. And the C library in Linux simply maps to the Linux system call interface and provides some additional functionality in between so that it becomes more convenient to use. But in the end, it maps to Linux system calls. And at this point, our part of the C library uses something different, which is emulation libraries. And in it, if you create an L4Re application, you get your C library, and the C library internally then links against different other libraries which provide certain functionalities. For instance, there is a virtual file system library that is linked into your application, and the virtual file system library provides your application with a view on some kind of a virtual file system. So you have directories and files and all that stuff, and maps the standard file system calls such as open, read, write, close to calls to a file system server that's providing real access to the files. So for your application, it looks like you're using the C library's functionality to access a file. However, the VFS emulation library maps the C library calls to IPC calls to a file system server. And you can have a similar thing to, for instance, for a socket library, which would map socket calls such as bind and accept and listen and so on to a TCP/IP server. What this gives you is you can write your applications and expect the C library interface to be available without needing to know about the complex system below. And on the other hand, it gives us the flexibility to implement microkernel services at dedicated user applications as we want, and have applications call into them at their will. I'm going to explain you now how this works in more detail for the POSIX C library. POSIX, as you probably know, is the portable operating system interface for Unix. It's a standard, and the standard defines services that a C library or an operating system need to provide. And provides, for instance, interfaces for I/O, such as files, sockets, and terminals. And it also provides a specification on how threads work, which is implemented in the pthread. And it provides a couple of other interfaces. And these are commonly defined, and all Unix and Linux operating systems provide a POSIX-like system call interface. And even Windows has some kind of a subsystem that provides POSIX functionality on Windows. So that if you write your application that uses the POSIX C library, then you can be sure that it's going to run on most systems that are POSIX compliant. Usually the POSIX functionality is provided by a C library, and if you have a closer look at what such a C library provides us with, then we see that there are different layers of abstractions or dependencies on the underlying operating system. So the best thing porting a C library are the parts where you don't need to do anything because they don't have any dependencies and they simply use functionality provided by the CPU. And these are, for instance, memcopy and string copy and all those routines, which simply work on pieces of memory, which are somewhere there, and which then simply use some kind of CPU-provided instructions for performing this task efficiently. Then if we go one layer of complexity up, then we have functions such as malloc, which implement memory allocation. And malloc is actually implemented inside the C library, and if you go into the implementation, then there's a lot of code you can reuse. However, at some point, your malloc implementation is going to use a system call in order to obtain memory from the system itself. And this is going to be when it calls system calls such as mmap or sbreak, which are provided by standard Unix systems. And so the part here is that the whole implementation of malloc can simply be reused in L4Re as well. However, at some point we need to hook mmap or sbreak or whatever into L4Re style of managing memory. Sorry. So the most complex things are interfaces provided by or defined by POSIX, such as get password entry, which makes a lot of assumptions about the system. So get password entry basically assumes that your system has a file called etc passvd. It assumes that there is some kind of user notion, so you have users on your system. It assumes that there's POSIX-like access control lists for managing access to files, and of course also assumes that there is a file system implementing this whole stuff. And these are a lot of dependencies, and most of the time you don't find all of them on your microkernel-based systems. So you have the option then to either emulate this behavior or to simply leave those functions away because your applications are not going to use them anyway. And depending on what functions it is, we do one thing or the other. So here's a comparison how POSIX is implemented in Linux in comparison to L4Re. So on the left side we have a Linux application. Usually your Linux application is linked against glibc, and glibc then uses some system call bindings also written in C and assembly to talk to the kernel. And then you have the kernel providing system call entry code, and the system call entry code would then, for instance, map file-related system calls to Linux VFS layer. The VFS layer would then hook into your file system implementations such as X4 or FAT, and then down below you'd have device driver and all stuff down to the hardware. So your glibc would provide you with the standard C and POSIX functions you would expect, such as memcopy, fopen, get time of day, and so on, which is implemented over here. Then you use a system call interface, which provides you system calls such as open, close, read, and mmap. And then the rest of the stuff is implemented inside your Linux kernel. As we do all those stuff in user space, what we have in L4Re on the right side is we have the Fiasco.OC microkernel, and on top of that we have our basic resource manager, we have device drivers, we might have file system servers, real-time clock, and so on. And you have your application that's going to use those. So first thing we do is we link our applications against the C library. In our case it's the uclibc, which again provides the same interface as glibc provides on Linux. In addition to that, instead of using some kind of open, close, and so on system calls, we provide the system call level functionality in additional L4 libraries for certain tasks. So there's an L4Re memory library, there's an L4Re virtual file system mapping to different file system implementations, there's an L4Re timing backend talking to a real-time clock, and we call those libraries backends. So uclibc is nearly unmodified. The only place where we modify it is where we hook directly into L4. And this is usually the place where a standard C library would to perform system calls. And we replace the places where system calls are performed with calls and functions provided by our backend libraries. And the backend libraries then are implemented by ourselves, so they have knowledge about the services that are in the system and the interfaces they use. And so, for instance, the L4Re memory backend would map C-style memory allocation to calls to an L4 memory allocator using interfaces such as L4Re memalloc, for instance. And the L4Re virtual file system would use calls like VFS open to open a file on a ROM file system or on an X4 file system if you have something like that. So the main point to take away here is, while on a standard Linux system, most of the complexity is hidden behind the Linux kernel, and you simply use the C library. In L4Re, you use the same interface provided by the C library, but you link against different other libraries that actually hook your C library up with the service provided in the L4Re system. Here's an example of such an L4Re backend. This is for implementing the C time function. And basically what we do is we provide a separate implementation for time, and so we replace uclibc's original implementation with our own. And this implementation simply calls an L4 function called libc vert clock get time, which is pretty much this L4 way of obtaining the time, and then returns the return value from there. And then we have this L4Re specific backend function, which implement accessing the clock in an L4 system. And here's the L4 specific functionality, and this basically ends up having a look at the clock field, which is provided by the kernel info page. Remember, the kernel info page is a page that's mapped into all applications and allows them to obtain certain knowledge about the system, such as what kernel am I running on, what is the system call entry code. And in addition to that, the L4Re kernel info page also provides a field called clock, which allows you to obtain the clock value at the last point you were scheduled. And this is pretty accurate in order to get your current time. So turns out we have a specific implementation for obtaining time that is hooked into the C library by replacing the implementation of the C library's time function, and the functionality is split across libraries. So the time function is implemented in the C library, and this RT clock get time is implemented in an L4Re specific backend library for accessing the time slot. Here's another example for mmap. I already told you that the C library usually implements some kind of memory allocator, and from a 10,000 feet point of view, this basically means that your C library somehow obtains memory mapping from the kernel, usually using something like mmap with the map anonymous and map private flags set, and thereby it obtains a large chunk, like a couple of megabytes of memory, and then implements a memory allocator on top of that. So whenever you call malloc, you're not ending up calling the kernel, but the C library reuses this chunk of memory and gives you some piece of this inside there. And only when the C library finds out that this chunk of memory has been used and is completely handed out to your application, then it uses mmap again to obtain more memory. So the whole functionality of working on a chunk of memory and allocating smaller pieces of them to the application when it calls malloc is reusable. We can simply use the same functionality if we find a way to allocate this chunk the C library expects when it calls mmap. And in our case, this is implemented in the L4Re virtual file system library, which implements mmap because mmap actually is a file operation. And there's a special case handling in L4 in the virtual file system library that figures out that if mmap is called with the map private and map anonymous flags set, then basically we obtain an L4 data space using the memory allocator, and this L4 data space is then attached to your memory, and then the C library's memory allocator implementation can simply use this data space as the chunk it operates on. And then we can reuse the L4, the ellipses memory allocation implementation. So to sum things up about legacy reuse, L4Re provides you with a standard C and C++ library that provides you with POSIX functionality and the standard C++ library with the standard template library and so on. And we solve this problem, or we allow this, by reusing the implementation of such libraries and only mapping the OS-specific part. It calls to additional backend libraries which provide you functionality such as a virtual file system, memory allocation, timing, signals, sockets. It's all there if you need it. The good news is that if you have such a POSIX interface, then you directly enable a wide range of other libraries which are also available on L4Re, such as libpng for rendering images, or FreeType for rendering fonts, libcairo for drawing graphics. We have a Qt port to L4Re as well. So all that stuff simply depends on a POSIX interface, and as we have a POSIX interface, we can simply, or nearly simply, port those libraries as well. So POSIX is an important enabler for reusing existing software and simply compiling it for your system. But now, go on. What we have now is we can reuse the C library. We have a virtual file system. However, in the end, at some point, your virtual file system needs to map its calls to your actual hard disk. Network file system. You want to use your USB webcam to do imaging. What we still device driver that provides. So I was talking about device drivers, and that in the end you need access to a hardware device at some point, and this means you somehow need to operate on hardware resources and provide an interface to access them. And if you think about microkernel philosophy, then we know that any non-essential components that aren't really required to run in privileged mode should be run in user space. And we're having kind of a problem here because on the one side, device drivers need to access hardware, and this sometimes means that you need to have privileged access to hardware because only in privileged mode you can do certain things. On the other hand, a device driver for your network device is not necessarily essential for your system if you're never using the network interface. So you don't want to put this into the kernel so that everyone would depend on it. So in the next part of the lecture, I'm going to introduce you how we handle device drivers in L4. But before that, I'd like to give you some motivation. And so there are a couple of papers out there that describe the influence device drivers have on operating system. And there's one standard paper that says that device drivers cause statistically 85% of all Windows XP crashes. So in 85% of the times where you saw a Windows XP blue screen of death, you basically blame Microsoft, but actually you'd have to blame the hardware vendor or the device driver writer because it was the device driver's fault to crash the system. There are some more detailed analysis. For instance, there's a paper from 10 years ago called Faults in Linux, where they had a look at the Linux source code, how it evolved from version 1.0 until 2.4, and evaluated how many errors you had in certain files, how long those errors lived, and so on. And they figured out that for one, Linux device drivers are 3 times more error prone than the rest of the Linux kernel. They also found that bugs cluster, which means that if you have a fault in one C file, then you're pretty likely to find another fault in the same C file, which they attribute to the reason that people usually write this code closely in one file. So if someone made a mistake at one location, he's likely to have made another mistake as well. And they also found out that the average bug expectancy for a bug in the Linux kernel at the time of version 2.4 was 1.8 years. So it takes 1.8 years for a bug in average to be included into the kernel and until it is fixed by a patch. Interestingly, there has been a repetition of this paper last year, which tried to figure out if things have changed over time. And it actually didn't. They found out that device drivers are still the most vulnerable part of the system, even though file system implementations are actually catching up. And they also found that the average bug expectancy of a bug is still about 2 years. So things haven't really changed at that rate, and device drivers are a pretty evil thing. In the last paper, some guy called Leonid Brzyk did an analysis of what the causes for device drivers bugs are. And they had a look at bug reports for certain device drivers in Linux and classified them into what was wrong with this bug. And they figured out that like in a quarter of the cases, it was an actual programming error where someone didn't understand how C works and made something wrong. But this is only a quarter, and the rest of the mistakes were either someone misunderstood the device specification, which means the hardware vendor provides you with some kind of specification, like if you write to a certain register on the hardware, then something happens, and if you make an error regarding that place, then that's a bug in your driver. And the other half of the errors were where the device driver writers actually did not understand how the operating system driver interface works. So this includes bugs, for instance, where the driver tries to allocate memory using kmalloc in Linux and passes the wrong flag. For instance, if you want to have DMA memory and you allocate memory that is not DMA-able, and so on. So what we can take away from that is that the most important issues are that either device driver writers do not understand the kernel, because they are hardware vendors and they know the hardware, but they don't really know about the operating system. And the other way around, if device drivers are written by operating system people, then they use or know about the operating system interface, but they don't understand how the hardware actually works. And this makes things pretty error prone. I'm going to give you one little anecdote to show you how long it takes to figure out what actually happens in such a bug. And it's a story from 2008. It's actually 4 years ago. Well, there was the Intel E1000 PCI Express network cards, and they were in a couple of modern laptops at this time, and they broke in Linux 2.6.27. And what happened was that people started reporting, I'm having this E1000 network card and it doesn't work anymore. And what they meant by it doesn't work, it was really it didn't work anymore. It didn't do anything. You could reboot your system and the network card wouldn't respond anymore, nothing happened. And after some investigation, in August 2008, people found out, okay, someone overrode the non-volatile RAM on the card, which was used to store the card's configuration settings. And if you overwrote it with some arbitrary values, then you basically broke your card and rendered it useless. Nearly 2 months later, Intel finally came up with a quick fix. And this quick fix was to simply map the configuration RAM of the network interface to some other address in the kernel's virtual address space. So this is only a quick fix. This is not the actual solution, because we still don't know what the reason for this problem is. But they figured out, okay, if I map the RAM to some other place, then at least the error doesn't occur anymore. It took them some more time, 2 weeks more, until they found the actual reason for this error. And the actual reason was dynamic function tracing. If you don't know what this is, dynamic function tracing is a Linux kernel feature that allows you to patch the kernel in order to trace calls to certain functions. So it's some kind of a debugging feature for the kernel. Totally unrelated to network interface cards, by the way. But what dynamic ftrace does is it collects a list of all the function entry points in the kernel when you boot the system. And then later on, if you want to instrument such a function, then dynamic ftrace patches the actual code. But at boot time, it only collects this list. The problem was here that it ran during boot time, and it also found functions that were in init code, which are the sections, for instance, where drivers have certain init functions that are initialized during boot up, and after the initialization has gone through, the init sections are mapped away, because you don't need them afterwards anymore. So what happened was dynamic ftrace found the functions in init sections, then the rest of the boot ran through, and then the init sections were unmapped, which means the memory was freed again and someone else could use it. And what happened was that actually the Linux E1000 PCI driver mapped the non-volatile RAM to a location that was previously used by init code from some other driver. And this is how dynamic ftrace figured out, okay, there is some function in there, and then later on dynamic ftrace started patching the functions it found. So it started writing to those locations where it found a function entry in an init section, for instance. And unfortunately, because the init section had been unmapped and the NV RAM had been mapped into this location, dynamic ftrace actually overrode parts of the non-volatile RAM from the network card. Of course, the dynamic ftrace people aren't stupid, and they tried to figure out, or they tried to be defensive and try to find out that if someone unmaps code before I patch it, I want to figure out that there actually is something different now, and I don't want to patch it anymore then. And they used compare exchange for that, which means they knew, okay, there should be this operation in the code, and I want to patch it, and they used compare exchange and only exchange the value if the comparison tells you that there's still this old value. However, compare exchange on x86 is undefined for I/O memory, and the non-volatile RAM of the network interface is actually I/O memory. And if you do a compare exchange, you're not guaranteed that the write only goes through if the actual value you want to see there is there. So in this case, it actually wasn't, and they overwrote the non-volatile RAM, and things went downwards from then. So the last piece is then that on November 2nd, which is like 3 months after the original bug report, dynamic ftrace had been improved for Linux 2.6.28. And so what we see here is this is one device driver bug, or actually it isn't even a device driver bug. It's a bug in a subsystem that has access to the rest of the system, including device drivers. And it took really a lot of clever people 3 months to figure out what's going on there and how to fix this problem. And if you count the number of driver bugs, like there are surely thousands in the Linux kernel, and if you sum that up, you see that you're not going to end up with driver bugs fixed anytime soon. So the idea here is, or the idea to solve this is to run device drivers in user space instead of the kernel, because then kernel subsystems would not be able to access the driver and do something evil if they're not supposed to do that. This gives you additional isolation, so you can have device drivers running in separate address spaces, giving you could have your disk driver, your network driver, whatever running in your own application. In addition to that, you can also access certain stacks that provide you with protocol or state machines to access the underlying drivers in additional applications. So you can have an application providing TCP/IP stack, or an application providing some kind of file system application. And by separating them from each other, they become more robust, because a failing component only can hurt itself, but not anyone else. However, if we want to do that, we end up with a couple of problems which we need to solve. So one is, if we run drivers in user space, we're going to see performance overhead, because we're context switching between those driver and the user applications all the time. We also see that we need to multiplex hardware, because there may be different applications that want to use the same device, and we somehow need to make them be unaware of other applications, because we want to add false isolations. And in addition to that, we have privileged hardware accesses, which we also need to solve, because otherwise we won't be able to communicate with our devices. So I'm going to go through the common hardware resources now, and the first hardware resources a driver needs to handle are interrupts. And interrupts are pretty much hardware lines that connect your hardware device to the CPU's chipset, and in your CPU at some point you have an interrupt controller, like a programmable interrupt controller called PIC, or then there's modern versions called APIC, where A stands for Advanced Programmable Interrupt Controller, and they actually map the hardware's interrupt lines to CPU IRQ lines, which then get triggered whenever hardware interrupts arise. And they do things like prioritizing the interrupts if you have multiple at the same time, and they also allow you to acknowledge an interrupt and mask it, mask it, so that you can be sure to not see an interrupt for a certain amount of time. So the good news is the PIC is there, so it's going to do most of the work for us. The bad news is accessing the programmable interrupt controller is actually a privileged operation, and only the kernel is allowed to do that. Which means, in turn, we need to have the kernel handle that and map it somehow to user-level applications. And what we do in L4 is we provide a kernel object called an IRQ object, which represents an interrupt. And the kernel maps every hardware interrupt to such an IRQ object. And in user space, you can then perform a system call called L4IRQ attach to signal that your current thread is wanting to receive interrupts from this interrupt line. And then you can wait for a message on this IRQ using L4IRQ receive. So this way, what happens here is every hardware interrupt is mapped to a kernel level IRQ object, and exactly one thread in user space can attach to such an object and can then receive interrupts on such an interrupt object. So thereby you basically get delivered the hardware interrupt to your user level driver. One problem we have here is that sometimes some drivers might want to have multiple IRQs, because, for instance, your network card is providing you with 2 different IRQ lines or something. In this case, you can simply attach to multiple IRQ objects and do an IPC wait, which is an open wait, giving you a message whenever one of those IRQ objects raises an interrupt. The other way around, there may also be IRQs that are shared among devices. For instance, your network card and your hard disk might be attached to the same CPU interrupt line. In this case, you can create software level IAQ objects which can be chained to a master hardware IAQ object. And then you can perform standard IAQ chaining as you would in Linux, where like your first device driver gets asked, is this an interrupt for you? And can then say either, yeah, it was my interrupt and I'm done handling it, or it can say, it wasn't for me, and then the next IAQ object in the chain is triggered and the next driver is asked if it is responsible for handling a certain interrupt. So to sum things up, interrupts in L4 are mapped to kernel objects called IAQs, and these kernel objects basically map interrupts to IPC, and you can handle them just as you would. The next hardware resource that is available and which is specific to x86 are I/O ports. And I/O ports are pretty much a new address space that is orthogonal to the physical address space. So you have 65,000 I/O ports in your system, and you access them using special instructions called in and out. And for instance, usually the serial port is accessed through such an I/O port on x86, and there's a magic address called which is 3F8 hex, and this address is then is the address of the serial port usually. And if you want to read a byte from the serial port, you'd use the in instruction to read this byte actually. The thing to take away here is that there is no virtualization in between. So in memory we have physical memory and we have virtual memory, and we have an MMU in your CPU that maps those things, and the kernel then manages different MMU contexts or page tables for every application. This is not the case for I/O ports. I/O ports are simply global addresses. And this means we somehow need to restrict access to I/O ports, because you don't want everyone to start poking on your network device if he is not the network driver. The good news is the in instructions and the out instructions are basically not privileged, so you can use them in user space. However, we need to somehow manage access to the I/O ports. Hardware, fortunately, provides us with a way to do so, which is called the I/O bitmap. And the I/O bitmap is basically a bitmap that contains one bit for every I/O port in the system. So if given 65,000 ports, this means the I/O bitmap is 8 kilobytes large. And whenever your kernel detects, or your hardware detects that a certain application tries to access an I/O port, it either checks if this application is currently running with an I/O privilege that is similar to the kernel. And if this is not the case, so if this is a normal user application, then it checks the I/O bitmap. And in the I/O bitmap, if a bit is set to 0, then you have access to this I/O port. If a bit is set to 1, then you don't have access, and the CPU raises general protection fault. The good thing is you can modify the I/O bitmap, and you can actually have one I/O bitmap for every task in the system. Because the I/O bitmap is simply referred to by a pointer in the task state segment, which is part of the underlying hardware. And what the Fiasco kernel does is whenever you switch between tasks, it also switches this I/O map base address. So for every task we have a separate I/O bitmap, and by default all bits in there are set to 1, so the task doesn't have access to any I/O port. And when you switch to another application, the other application's I/O bitmap pointer is loaded, and there may be different values set in there. So now that we have this mechanism, what we need is another mechanism that allows us to actually provide or allow tasks to get access to a certain I/O port range. And this is again done using IPC and flex pages. I described this to you in the last lecture, that for memory regions we can specify a certain region in memory, and then we can use a flex page descriptor which we put in the buffer registers in the UTCP, set it IPC, and the kernel will then adopt the page table of the sender and the receiver in order to reflect this mapping. And we can do the same thing now for I/O memory or for I/O ports by providing a specific format for I/O flex pages. And the difference here basically is that the highest 4 bits are different from memory flex pages. They are all set to 1. And in this case, the kernel figures out, okay, this is an I/O flex page mapping and not a memory mapping. and thereby it modifies not the CPU's page tables, but it modifies the I/O bitmap for the receiver task. And then again, flex pages work pretty much the same. So we have a base port where we want to start allowing access, and we give a size, so you can again specify certain ranges of I/O ports which you want to give access to someone else, and thereby the kernel will then adopt the I/O bitmap of the receiver, and the receiver may then use the in and out instructions to access those specific I/O ports. Again, we need some root in the system which has access to all I/O ports, so it can hand out this access, and this is the initial I/O memory. And in addition to I/O ports I was just talking about, I/O memory is simply physical memory that is somewhere on the device. So for instance, your graphics card has some memory to store images. Network cards have onboard memory for storing network packets as well. And this memory behaves like real physical memory. And your BIOS or your chipset also maps this hardware memory into the normal view of physical memory. So in physical memory you see your RAM memory as well as all the physical memory provided by interfaces. And then depending on what kind of hardware you're talking to, there is a specification on how this device memory looks like and how it works. And the good thing is, as it works as normal physical memory, you can simply reuse the CPU's virtual memory functionality to map it into, or to give it access to, or map it into a page table and into a virtual address space. And you don't need any special instructions for accessing them, and this is pretty easy, fits into the rest of the system. And on L4, we also fit it in by simply mapping stuff first to the kernel and then to the driver, and for the driver then it looks completely the same if it was accessing real memory or device memory. And actually the distinction, if you access a certain virtual address, which is then translated to a physical address by the CPU, and then only your CPU's chipset decides if your write to memory really goes to memory or if it goes to a device. And for your driver it simply looks like I obtained a certain data space, attach this data space to my virtual address space and simply use it as any other memory. Again, Sigma 0, the initial resource manager, initially gets access to all resources, so it also gets access to all I/O memory, and then may map different regions of I/O memory to different device drivers, for instance. So the point to take away here is I/O memory is pretty easy because we can simply integrate it with the memory management for the rest of the system. One last issue before we have a break is can I trust my driver? And so far I was only talking about device drivers as one device. However, usually devices are attached to something like a PCI bus, which basically connects all devices to your CPU, and then you have mechanisms that allow you to iterate over all the devices on the bus and figure out what device is there, what you can do it, which driver is responsible for this device, and so on. So what this requires you to do is you need to be able to actually iterate over all the devices. And especially in PCI, there is something called the PCI config space. And PCI config space basically allows you to figure out some information about all the devices that are attached to your PCI bus. And the only thing you need for doing this is you write a device address to a certain I/O port, and then you read the result from another I/O port. And this device address only consists of the bus number, a device number, and the function number. And you can basically brute force walk through all possible bus device function combinations and can start figuring out if there is a device attached to this certain address. And if it's not, the PCI config space will return you -1, so you will see that there is no device. And otherwise, you will find a device in there. And you will not be able to directly access this device because this is only information you obtain about the device. However, this may already be enough because this information contains things like a bit for enabling or disabling a device interrupt. So if you're malicious, you can already use PCI config space access to disable interrupts from a device and make it non-functional for the user. Additionally, you can also use the PCI config space to figure out what the actual hardware resources are this device uses. So what interrupt is this device attached to? What are the I/O port and I/O memory regions used by the device? All this information is available in the config space, and you have this information, you can then start simply accessing this I/O memory and thereby drive the device even though you might not be supposed to drive the device. So the problem here is, who makes sure that my driver only accesses the PCI config space of the device it is supposed to drive itself? And the solution to that is another service we provide in L4Re, which is called an I/O server. In this example down below here, we have our PCI bus, and the PCI bus has all the resources attached, or a couple of devices attached, like here's a network interface, there are 2 hard disks, and there's a sound card. And all of these devices have resources, which are the small squares in here. And they are all attached to the bus, and if you have access to the physical PCI bus, you can iterate over all those resources and figure them out. And the one component that is allowed to do this in L4Re is the I/O server. The I/O server initially scans all the devices and figures out what devices are there and what the resources are. And then the I/O server provides you with a functionality to generate virtual PCI buses that are then mapped to the respective device drivers. So what we do here is we create a virtual bus which only contains those devices a certain device driver is supposed to see. So for instance, the sound driver would get a virtual PCI bus that only has the sound card's resources attached. And thereby, the sound driver then can scan the virtual PCI bus, and the only thing it sees will be the resources for the sound card. This, of course, requires us to do some additional management. So actually, the sound driver must not use I/O port read and write to access the PCI config space anymore, but we need to map this I/O port read-write to IPC calls. However, this is fairly easy by simply not giving the device driver access to the I/O ports required to access the PCI config space. And then the only thing that the driver can do is actually use IPC calls to the I/O server to perform read and write to I/O ports. And the I/O server can then make sure that those will only return valid values if they go to a device that's on this virtual PCI bus the sound driver is supposed to access. So using the I/O server and virtual PCI buses, we can split or isolate devices that are on the same physical bus and make sure that our network driver does not start reading data from disk without our consent. This concludes the first half of my talk. So what we know now is that Fiasco and L4Re allow us to implement device drivers in user space, and the usual device resources are mapped to mechanisms provided by the kernel. So interrupts are mapped to communication messages, I/O ports are managed as a kernel resource using the I/O or the I/O bitmap, and you can delegate writes to I/O ports using specific I/O flex pages. I/O memory pretty easily integrates with memory management in general because I/O memory doesn't look different from physical memory to a kernel. And security issues such as resource scanning on the PCI bus are managed by a separate I/O server that allows us to isolate components from each other so that you only see certain hardware devices you're supposed to see. I suggest drivers. So given that we have those management and functionality for accessing hardware devices in user space, we can now go and implement a device driver just as in any other operating system. So you somehow access the hardware using those mechanisms. You specify a server interface because you're building a microkernel server around it, and then your users may use IPC to talk to your server, and the driver will then access the hardware. So far, so good. The good part is you can write highly optimized code, which is pretty fast. However, it becomes hard to maintain because you have to write everything from yourself. And we saw earlier that device drivers are actually really error prone, and of course you're going to make all those errors yourself as well. So it's going to be hard. Implementing device drivers for all the devices in your system is pretty time consuming because there are a lot of devices, and if you want your operating system to run on a lot of computers, then things get harder and harder. And it's also hardened by the fact that device vendors will not give you the specifications for free. So in order to write a device driver, you need to know how the device works and which are the registers you need to access in order to send a network packet, for instance. However, not all network interface vendors will give you the specification unless you pay them a lot of money. So that's making things harder again. People came up with this question, so why do I have to implement a device driver anyway? Because if you have a look at other operating systems like Linux or BSD or Windows, there are all those device drivers in there already. And why can't I just reuse them? I mean, in Linux and BSD I have the source code, in Windows I at least have binaries, so why can't I simply run them on my microkernel? And the basic idea to achieve this is to come up with some kind of glue code you wrap around your drivers. There's one implementation on Linux called NDIS wrapper, which was there to wrap some kind of a Windows-like interface around Wi-Fi drivers so that you could run them on Linux. And the idea to reusing device drivers on L4 is pretty much the same. You take the original driver, implement a library that's kind of pretending to implement the driver's host API, such as the Linux kernel API, and then map all those calls into the underlying system, in this case L4. The problem here is, of course, how do you implement this, but in the end it turns out you can do it. So our solution to that is called the device driver environment, or short DDE, and here's what it does. So you start with some kind of a donator driver, which for instance comes from Linux, and you have your host runtime environment such as L4Re. And what you want is you want your donator driver run on the environment, but the interfaces don't match. And what the DDE then does is it introduces another layer in between the driver and the host runtime environment, which communicates with the driver using the driver's expected interface and communicates with the host environment below. So it maps all the Linux calls to calls to the runtime environment at the bottom. We implemented this first for Linux, where basically what we do is we use multiple L4 threads to simulate some Linux-like environment. And those L4 threads then implement Linux functionalities such as work queues, software queues, bottom halves, timers, Linux Jiffy's feature to access the time, and so on. As we're running on multiple threads, we also need to make the Linux code feel like it's running on an SMP system, so that it uses locking at the right point in time. And then our DDE library provides functions that wrap certain Linux functionalities. So for instance, Linux kmalloc, which provides a memory allocation, is mapped to an L4 specific library that uses slab allocation below. Linux spinlogs are mapped to pthread mutexes in our case, because we are running in user space and we have those available already. And in addition to that, we map any kind of hardware access that's using certain Linux functions to L4 specific functions, such as accessing the PCI config space using IPC calls to the I/O server. The next step then, once you have this for Linux, is you say, I want to reuse another driver from another operating system, such as FreeBSD. And so what you can do is you can start implementing your own DDE for FreeBSD, which we did as well. And then you can use Linux drivers as well as FreeBSD drivers and map them to the runtime environment. However, it soon becomes inflexible, because then you start doing your DDE for Windows, which other people did. You do a DDE for whatever new operating system you want. Android maybe these days, even though Android is only Linux. And in the end, what you find out is that most of the functionality in those device driver environments is the same across all of them. And this was then the point where we decided to introduce another abstraction called the DDEkit, which provides a set of common functionality that all device driver environments needed. And so if you have a look at device drivers across separate systems, then you see all of them will use threads in order to perform multi-threading. They will all require some way of synchronization. They all need memory allocation. They all need to handle accesses to hardware resources such as IRQs or I/O ports. And this whole functionality is now put into a generic device driver environment construction kit called DDEkit. And then you only implement the donator operating system specific parts in a specific DDE for Linux or for FreeBSD or for Windows. The good thing is this makes the whole implementation smaller because you're reusing a lot of functionality from the DDEkit in your DDEs, and it gives you more flexibility. Because in addition to porting the higher part, where you provide a new interface so that you can use a donated driver on your system, you also can port it into the other direction. If you have a look at the whole DDEkit thing, here's a bunch of lines of code we saw. So our standalone device driver environment for Linux 2.4 was about 3,000 lines of code, which was only the library mapping Linux device driver calls to L4 calls. We now split this up to 2,000 lines of code, which are DDEkit, which is the generic part, and about 1,000 lines for DDE Linux 2.6, which is the current version of DDE. So if you sum this up, you still end up with the 3,000 lines of code you had in the earlier DDE. However, implementation of the next DDE for FreeBSD then will require you another 1,000 lines of code, and for Windows you probably need another 1,000, perhaps even more, because Windows has binary drivers and some stuff more. And the cool part on this slide is that if you compare this to a standalone Linux virtual machine, which you can strip down to only contain the driver you're interested in and that you want to communicate with, then this will be about 500,000 lines of code. And this is like 2 orders magnitude smaller in the DDE, which means we're less likely to have errors in our implementation and so on. And the other part is that this is highly customizable, because if you're only writing a disk driver, then you only need the disk-related functionality from Linux, and simply linking your DDE library against it will already strip away all the functionality that's not needed, because your linker is simply throwing away all the functions that are never called. So far for the DDEkit. I also indicated already that the DDEkit is portable in 2 directions. So one thing is you can implement donator device driver environments on top of DDEkit, which allows it to reuse different drivers from different sources. The other part is, once you have that, and because the device driver environments only use functionality provided the DDEkit, we can also start porting DDEkit across different operating systems. And this is also something that has been done. So we ported DDEkit to L4N, which was the predecessor of L4Re, and then we implemented it on top of L4Re as well. So we could use the same device drivers on both systems. The G-Node operating system framework, which Norman Feske is going to talk about in some future lectures, is also using the DDEkit approach to reuse device drivers. And there have also been ports of DDEkit to Minix 3, to the GNU herd, and to Linux user space as well. And in all those cases, you only need to port the DDEkit, and then you can simply reuse the whole DDE implementation on top of it, which in the end means you can actually use a FreeBSD device driver running in Linux user space on top of a Linux kernel using this approach, which makes it pretty flexible and portable. So what we now have is we can now take a Linux network driver, link it against our DDE and DDEkit libraries, and then we have a network server that's providing access to the network card. On top of that, we can have another application or the TCP stack that accesses the network driver and provides some kind of socket interface. And given that I told you about those backends in the beginning, we can have our C library that provides a socket interface and talks to the TCP stack using this L4Re socket backend. The question is now, how do we split things up in our system? If you want to have full protection by isolating the components, then the best thing you can do is to have everything run in its own application. So you have a user application running in a dedicated address space, then you have the TCP stack running in another address space, and you have your network device driver in its address space as well. And then you can use IPC communication between the application with the TCP stack and the TCP stack and the driver as well. However, the problem of isolation is that the performance sucks, because you're going to switch all the time when you send messages between the applications. You need to switch address spaces, which is pretty slow. You need to enter the kernel all the time. And the better way, if you want to achieve best performance, is something called co-location, where you put everything inside one address space, which our approach allows you as well. So you can have your application, link it against the TCP IP library, and then link it against DDE and DDEkit, which have the Linux network driver included. This way, you run everything in one application, which is faster because the communication between the simple components now simply becomes function calls instead of IPC, so you don't go through the kernel, you don't switch contexts all the time. However, you're less isolated and thereby more error prone now, because now if the driver crashes, then it can override any application state or a TCP IP state, whereas in the left scenario, when the driver crashes, it will only bring down the driver, but the TCP stack will remain intact and the application will remain intact as well. And depending on your use case, you can then decide what is more important for you, having the isolation or having good performance or having something in between. And our system simply allows you to do both. The last problem regarding devices I'd like to talk about is sharing between devices. What we have now is we have our network driver wrapped in a L4 user space server, and we can provide some kind of a server interface for the network driver, which an application might use. However, in many cases, we might have multiple applications that want to use the network, and so they all need to talk to the network service. However, devices often do not allow you to share state or to share the device without them knowing. So, for instance, a network interface, if we remain with this example, has a physical MAC address, and all Ethernet packets are sent to it given this physical MAC address, and the network device simply accepts incoming packets for this address. But what do you do then? How do you distinguish if a packet is for the left or the right application? And that is a problem actually, because this prevents you from having multiple applications which are isolated and can still use the network. The solution to this problem is to add, again, another layer of virtualization. And in our case, we extend the network server with an interface that provides virtual network interfaces to the applications. So every application uses its own virtual network interface, and then the virtual network interfaces are connected to the real server using a multiplexing layer. And in the case of networking, this is implemented in a component on L4 called ANC, which provides virtual network interfaces as kind of shared memory buffers between the application and the network driver, which makes this part of the communication rather fast. And for matters of multiplexing, ANC generates a random MAC address for every application that uses it. And by generating a random MAC address, we can send packets from this virtual MAC address, and then when network packets arrive at our network interface, the network interface will see, okay, this is a network packet for this random MAC address for the left application or for the random MAC address for the right application, and the multiplexing layer can then make sure that the packet is delivered to the proper application. Of course, this has the problem that your network interface must be willing to accept packets for different MAC addresses, which by default they don't do. Usually, if you launch a network interface in the standard way, it only accepts network packets for its hardware physical MAC address. However, most network devices support something called promiscuous mode, where you tell it explicitly, I want you to accept all packets regardless of what MAC address they have, and then you can do the multiplexing in user space and drop packets later on if you figure out they're not for you. Similar ways of sharing devices have also been implemented for input devices as well as for USB and for hard disks. I'm now coming to the last part of the lecture, which is going to be about virtual machines, because like the third way, or existing, are another way of reusing existing software on top of your new operating system. And they kind of perform a rather extreme approach to this reuse. Because you're not only taking your application and simply running it on the microkernel, but you wrap the application with the whole operating system into an isolated component, which is called a virtual machine. And for instance, if you want to reuse Windows application, you provide a virtual machine, and inside this VM, you run Windows, and on top of Windows, you can run then Windows applications. And in another virtual machine, you might run the Linux operating system along with Linux applications as well. The question is now, how do we implement this stuff? And this is what this last part of my lecture is going to be about. So usually, you have some way of managing virtual machines, and this is done by another component called the virtual machine monitor, which is sometimes also called a hypervisor. And in our case, we're running on a microkernel, so below that stuff, we will have the microkernel runtime and the microkernel itself. The good part about virtual machines is that they make reuse pretty easy, because you're providing the Windows applications you want to reuse with a real Windows environment, that you don't need to think about emulating calls and that stuff. The only thing that you need to emulate is the hardware, because you need to make the Windows guest operating system think that it is running on a real hardware machine. The other advantage is that you can then basically reuse any applications. There is no porting effort anymore. Once you're done with providing a virtual machine that runs the Windows kernel, then you can run any Windows application on top of it. However, there is still a problem. Someone needs to implement this layer in between. So someone needs to implement the virtual machine monitor and actually pretend that the hardware is implemented there. There have been a couple of tries at how to implement virtualization, and the ultimate goal here is you want to run your guest operating system, such as Windows, and you want to pretend that this guest operating system runs on real hardware and should not be able to notice that actually it's running in a virtual machine. The first try in doing so is emulation, which means you take a binary and figure out where to start, and then you find an instruction there, and you start emulating every instruction one after another. You have a look at the instruction, do decoding, figure out how this instruction would modify your virtual hardware, and then apply these modifications inside your emulator. The problem with this approach is that it is very, very slow. If you have ever used Box in comparison to QEMU, then you know what this means. Because Box is actually using this emulation approach, whereas QEMU is using something different. I'm going to tell you later. The good part about emulation is that because you're not relying on physical hardware to be available, you can also use it to emulate an Android phone on top of your Windows PC, for instance. Because then simply your emulator pretends to be an ARM CPU which is running Android, and you can run this emulator then on Windows and develop your software, and everything's going to work fine. One way to improve performance for virtualization is an approach called trap and emulate. Trap and emulate works for the specific case where your guest hardware and your host hardware are the same. So there's some terminology here. Host always refers to the machine you're actually running your virtual machines on, whereas guest always refers to the operating system that you're running inside the virtual machine. And if you have an operating system that is built for running on x86 and you're running on a real x86 virtual machine, then you can use an approach called trap and emulate. And trap and emulate assumes that your real processor can execute instructions in unprivileged mode as long as it is unprivileged, and only at the points where you actually need to perform privileged modifications to the hardware, you want to notify your VMM. So as long as you're only computing stuff in user space, simply reuse the real processor, which is the fastest thing you can do, and only at the point where your processor raises some kind of trap because you're modifying the page table or because you're accessing hardware, then you want your VMM to be notified, and then the VMM needs to handle those traps and emulate the behavior so that everything works as proper. This has the advantage of being really fast as long as you're executing in user space, so it's faster than emulation. However, it has the disadvantage that you need to make your CPU trap at all points that you are interested in. This means, for instance, that all instructions that perform certain operations in privileged mode need to cause a CPU trap so that you can notify your VMM, which means your instruction set needs to be virtualizable. That's what the notion is. And unfortunately, x86 in its original version is not virtualizable. And the reason is that there are some instructions on x86 which behave differently when you execute them in user mode or in kernel mode. One such instruction is the pop flex instruction, which normally would give you the current CPU flex of your machine. However, in user mode, it gives you only a subset of the CPU flex and not the whole stuff, which has the problem that you cannot disable interrupts, for instance. Because disabling interrupts means actually calling pop flex with one of the bits, the interrupt disable bit, set. And if you do it in user space, it simply doesn't do anything. So you simply execute the instruction, but you don't disable interrupts, and you don't get any notification about that. Whereas if you do this in kernel mode, then interrupts become disabled. So the problem now is we cannot simply trap and emulate x86 because of such instructions. A lot more. They are called the virtualization gaps, and close those virtualization gaps onto virtual machines in trap and emulate on top of x86. There have been two ways of fixing the problem. The first way was rewrite. I was talking about broken instruction set, and x86 has this problem that you cannot virtualize it easily because some instructions behave differently in user and privileged mode, and you need to make them raise a trap whenever they're executed in user mode and should be executing in privileged mode. The first thing to do was what VMware did in its early products, and it still is doing to some extent today. And it takes the guest operating system's binary and rewrites this binary into some other binary where all the broken instructions are replaced with something that definitely traps into the VMM. And by doing so, you can implement a pretty fast virtualization layer that traps all the time, fixes the broken instruction set, and then you can virtualize x86. However, of course, the binary rewriting phase is not as easy because rewriting binary code is there's a lot of complexity in there, takes some time, so it's kind of not the real way you want to go. So this is why hardware vendors such as Intel and AMD provide some additional technique today by adding hardware features to their processors, which on Intel is called VT, on AMD it's called AMD-V, and these virtualization extensions are kind of hardware extensions that make sure that basically all those instructions that would behave differently now raise or behave the same way on all and cause traps when they're executed in user mode. And using this hardware-assisted virtualization allows you to implement pretty fast virtual machines, and it fixes all those problems with the previous instruction sets. So the next question is, now that we have all those possibilities for implementing the virtual machine monitor, how do we do this? And there are basically three approaches which we distinguish. The one on the left is called the bare metal VMM, where actually your host operating system behaves or also acts as the virtual machine monitor. So you build virtualization into the host operating system. The good part is that your virtual machine monitor then runs on bare metal hardware without any operating system and any performance overhead caused by switching between the VMM and the operating system. It gives you complete control about the hardware and over everything that's going on in the system. The problem is that the effort of implementing such a VMM is pretty high because you need to do all the stuff yourself. You don't only need to take care of implementing the virtual machine, but you also need to manage the underlying hardware because you don't have another operating system in between. So this is why people said we do the thing in the middle, which is we run the virtual machine monitor as a user-level component on top of some other operating system, which allows us to reuse the operating system's infrastructure for managing memory, talking to the hardware, and so on, and concentrate fully on the aspect of implementing the virtual machine, which may have some worse performance than a bare metal VMM, but implementing such a VMM is much easier. And then there's the last part, where we actually remove the VMM completely. So it's kind of difficult because I told you that virtual machines are managed by virtual machine monitors. However, there's one way, which is the thing on the right, called para-virtualization, where you don't need a virtual machine monitor at all. Instead, you take your guest operating system and modify the guest operating system. So at some point, the guest operating system is going to access the physical hardware. And you now replace all those points where it would access the physical hardware with calls to an underlying operating system, like calls to L4 memory management, calls to L4 device drivers, for instance. And thereby, you make your guest operating system completely unaware of physical hardware and pretend that the guest operating system has been written to run directly on your host operating system. This has a couple of advantages. For instance, you don't have any overhead introduced by the virtual machine monitor. Your guest operating system is directly talking to the host OS, is directly running on the physical hardware, so it becomes pretty fast. The difficulty is that, of course, modifying the guest operating system requires you to have access to the source code of the guest operating system. So doing this for Windows would be a bit hard. And even for Linux, where you have this access, it still requires you to have a pretty good understanding of what's going on inside Linux in order to adapt Linux to run on the host operating system. So these are the three ways you can build virtual machines. One example for a bare metal virtual machine is the Nova hypervisor that has been implemented in Dresden, and I gave a link to one of the papers about Nova in one of the last slides. The thing in the middle, the user-level virtual machine monitor, is what we have already been using when you started L4 on QEMU, because then QEMU was the user-level virtual machine monitor running on top of your Linux host operating system. This can be done using different ways. So QEMU initially used binary rewriting, but these days also benefits from hardware virtualization when you combine it with KVM in Linux. And in the rest of my talk today, I'm going to talk about para-virtualization, because this is one of the things we did with Linux over here in Dresden. So let's start with the original Linux picture and see what we need to do in order to para-virtualize it. So usually what we have is we have applications running on Linux, and we have this whole monolithic operating system providing system calls and accessing the hardware. And if we want to virtualize this, we need to modify the hardware part in order to not directly talk to the hardware, but to talk to the kernel, to the microkernel below. And we need to modify the system call interface, because we need to somehow translate the application mechanism of performing system calls to a way that works with our virtualized way. So here's what we do as in L4 Linux. L4 Linux is our para-virtualized version of Linux running as a user application on L4 Fiasco. We wrap the original Linux applications as L4 tasks, so they become schedulable entities for the Fiasco microkernel. So the whole scheduling is performed down here and not in Linux anymore. And we also make the Linux kernel an L4 task. And what we need to do then is we need to have a new hardware architecture for L4Re, which you can simply do by modifying the Linux kernel. And then in Linux you already have architectures for different CPUs like PowerPC, x86, ARM, and so on. And you simply introduce a new ARC subdirectory in the Linux kernel that works based on L4. And at the top end, for the system interface, come up with a feature that maps systems from tasks to IPC in the task and Linux kernel task. So it's the A-level Bjoern implement that's more difficult, but that's how it goes. So I already told it should use L4. the new platform in Linux. Okay. More time.
Yes.
So, L4 Linux. We introduced this new hardware platform called L4 in Linux into the kernel, and we lay a couple of things through Fiasco actually. So thread switching is performed by Fiasco, as well as managing thread state, and the Linux will make sure that all the runnable threads are actually scheduled by Fiasco. We need to handle the MMU in Fiasco, because Fiasco is the actual privileged kernel that's able to modify page tables. So we need to reuse the Fiasco memory management mechanisms down there. Also, interrupts Linux interrupt handling is mapped to Fiasco style IQ object. And then for the other part, Linux applications are run as L4 tasks, and they use APC for entering the kernel, for delivering signals, and also for copying data between kernel and user space, because now in Linux, the Linux task and the Linux kernel are not running in the same address space anymore, which is the case in normal Linux, so you need to have additional ways of copying data between user space and kernel space. Here's how pre and exit work. In a traditional Linux application, you indicate that you want to perform a system call to Linux kernel using the int ADHex instruction. In Fiasco, this basically leads to a CPU exception, as it would on Linux as well. However, Fiasco cannot handle this instruction because it does not know about the int or about this interrupt vector ADHex. So what it sees is I receive a CPU trap, and then Fiasco relates this trap to user level handler. This works pretty similar to page fault handling, as I described you the last lecture. And similar to that every thread in Fiasco or setup has a page fault handler, it also has an exception handler thread assigned. And this exception handler thread receives an IPC message set up by the kernel whenever this thread raises an exception. And executing int ADX simply works as raising an exception and delivering an IPC message to the exception handler thread. The message generated looks similar to a page fault message, but contains additional state. So for an exception message, the Fiasco kernel will give you the whole CPU state of the faulty thread, which in turn means we can use this for system calls. We can simply make the Linux kernel the exception handler for all Linux user threads, and whenever they execute a system call, an IPC message is going to be set up by the kernel, delivered to the Linux kernel thread, and then you then you are in the Linux kernel and you can perform system call handling as you would in the normal Linux kernel. And this is pretty much all that it to handle or implement system calls in Linux. So after handling the system call, the kernel task then replies to this exception message, and the kernel makes sure that the Linux user level thread continues execution. One last thing is that it came up with an additional mechanism in Fiasco that simplifies the way exception handling works. Because if we have a look at it, so there are different ways of exceptions that we need to deliver between L4 and Linux applications. So there are system calls, there are Linux signals, there are inputs, and they somehow differ slightly in how they are handled. However, the mechanism is pretty much the same. And this mechanism is now abstracted in something on Fiasco called a virtual CPU, or short vCPU. And a vCPU is nothing more than a thread with some properties attached. And these properties are, there is a task and there's a task. And there's a new system or vCPU objects called L4 resume. And the resume system call basically says, okay, take this vCPU and start executing. I was talking about the vCPU model. So vCPU is simply a thread that has a kernel and a user task. And when you use the vCPU resume system call, you move this thread to its user task and start executing on the physical CPU, and nothing is going to happen. However, once this task raises a CPU exception by causing a page fault, or by causing a system call, or by causing any kind of other hardware-related traffic, then the CPU exception is delivered to the Fiasco kernel, and the Fiasco kernel will then move the vCPU thread from the user task to its kernel task. So thereby we easily end up with inside our kernel and already have all the state attached, because the virtual CPU has a whole set of CPU registers that belong to this thread stored inside it. And then again, we now end up in the Linux kernel, can handle this CPU exception, having a look at those registers, and then at some point it calls L4 vCPU resume again, and then the vCPU is moved back to the user task and continues executing user code in there. This whole mechanism has the advantage that it simplifies the implementation of L4 Linux, because we're now using the same mechanism for handling interrupts, for handling page faults, for handling system calls, and so on. And this pretty much concludes my talk. I'm going to talk about the third assignment a bit more. So in the third assignment, we're going to try out L4 Linux. And what we now want to have is something on have Linux applications running on L4 Linux, which is pretty easy. You're just going to download and build it. And now we want to make an external application running on top of L4 accessible to such a Linux application. So, and as the example application, we're going to use the server you implemented in the second assignment. And we now want to call the server not from another L4 application, but from an application running on Linux. The easy thing would, of course, be to use a Linux application and perform a system call doing IPC to the L4 application. However, our Linux applications are, as the name says, Linux applications, and Linux applications are not allowed to perform Fiasco system calls. Instead, the only thing you can do is perform a Linux system call and talk to the Linux kernel. So what we need in order to communicate with the external crypto server is a setup like this, where we implement a device driver that's running inside L4 Linux and implements a device, a character device for instance, in Linux, so that you have dev L4 crypt for instance, and then you can read and write to this character device in order to communicate between your Linux applications and the driver. And the driver itself then is running inside L4 Linux, which is of course an L4 application. And the driver can then perform IPC to the crypto server externally and exchange messages. So you're adding an indirection here in order to make this accessible to Linux applications. That's the whole view. Let's see what we need to do. So the first thing is you need to download and build L4 Linux. For that, you will use your existing L4Re checkout, because you're going to use all those components to run L4 Linux again. But you'll need a bunch of additional packages which are there in Subversion. However, they were not checked out yet with the default checkout. There are two ways of finding out which packages you need. One way is you just start building L4 Linux, and at some point L4 Linux will complain about missing libraries or about missing services, and then you figure out, okay, I need to check out another package. The second way might be easier. So here's the list I came up with that I had to check out in order to run L4 Linux. So these are all the packages that you need to additionally check out in your L4 runtime environment. And of course you need to build the whole L4 runtime environment before you can build L4 Linux. Once you're done with that, you can configure and build L4 Linux. The detailed instructions are described on the webpage. Basically, the configuration is separated into L4 specific L4 Linux options and options which are similar, which simply come from the L4 Linux kernel compile options. For the L4 part, please simply leave all the options as they are. However, there's one option that requires you to set a directory where your L4Re build directory is. This is the one option you need to modify. For the other part, in order to make compilation faster and to save us a lot of hassles, please disable as many hardware options in your Linux configuration as you can. So disable PCI access and all those disk access, disable networking. You won't need it for the example. Fundamentally, L4 Linux supports all those stuff. However, it's harder to get things running right now. You just want to have a fast setup that's able to communicate inside L4. So then you compile a build L4 Linux, and then you need to run it. Again, there are examples already in the L4 runtime environment. So you have this 4conf examples directory, which contains two important files. One is the L4Re86.io script, which is a configuration file for the I/O server, which I talked about in the device driver part, and makes sure that your Linux sees all the devices it needs to see, like the PS2 input, the frame buffer, and so on. It also would see all the PCI devices in your system, but please disable PCI in order to make things easier for the beginning. The second thing is L4LX-gfx.config, which is the Lua init script to launch L4 Linux and the graphical console, which you can work with. So, and there's also an entry in the L4conf modules.lst, which uses this config entry and the I/O script. And then you basically launch an L4 Linux. You will get a window containing, showing this Linux penguin and giving you a shell which you can work on. And then this is basically plain Linux running with a shell, and you can run arbitrary Linux commands on it. In order to do so, you need one additional thing, which is a root file system. And there you can do one of two things. One of this, we have a download link where you can download a RAM disk containing a pretty small Linux setup that's basically BusyBox with a couple of extensions. Alternatively, you could also build your own init RAM disk. There are tutorials on the internet. You may try this out if you want. But if you just want to have something prepared, then just download the RAM disk, which we provide in our download directory. And this root file system then will provide you with all the functionality you're used from Linux, like the shell and ls and all those other commands. And once you have L4 Linux up and running, you need to implement the device driver. And from the Linux perspective, this pretty much works as implementing any other Linux device driver. So you build it like any other device driver, and in Linux you can register a character device and then implement file operations for this character device in order to read and write data between user mode and the Linux kernel. And on the L4 side, the interesting part is that for L4 Linux kernel modules, you can pretty much use any L4 headers as you can use them in other L4 applications. So as long as they are C headers, that's the important part, simply include them, and most of the time they will be there. If there is a problem where you're missing a header file, then just notify us in the forums and we're going to find a solution, but it's not likely that you're going to see them. For communicating with the external crypto server, please use IPC again. However, notice that Linux is C code, and because Linux is C code, you cannot use C++ IPC streaming, but instead you have to manually write data into the UTCP and call the respective L4 system calls, which is the stuff you basically did in the first assignment, so you know how it works. Simply need to do it for your crypto server now. Yeah, okay, that's pretty much it. There's a final rule which you should obey, and this is if you're setting this system call up and send the IPC message to your server, please do not perform any other L4 system call in between writing data to your UTCP and performing the L4 IPC send operation or whatever you use. Log output, such as using print K and stuff, is an L4 system call. So the problem here is what you are doing is you're interfacing with the kernel directly. You're writing data into the UTCP to add system call parameters, however, and then you perform a system call. However, if you somewhere in between have a print K, you're going to perform another system call in between. And this other system call is going to override all the state modifications to the UTCP that you did before performing the system call. And so in the end, you're going to see different results than you would if you left this out. So it's just something to keep in mind, because when I tried out this assignment, I actually ran into this problem, and it took me some time to figure out what's going wrong there. So just to save you some issues, that's the rule to follow. Okay, finally some more papers. If you want to know details about more stuff. So there's one paper called Generic User Level PCI Drivers, where we describe the DDE approach and how we ported it to Linux user space device drivers. The second paper, called Generic Virtualization with Virtual Processors, gives a more detailed overview about how the vCPU model works and how it is used in L4 Linux. The third paper, called Nova, is a description of a bare metal VMM implemented here in Dresden, which is pretty small and pretty fast. And the last part concerns splitting applications in order to increase security. This is pretty much what you're doing in the third assignment. Is you can split up an application. You have the Linux user part, where you implement at your convenience and use all the Linux services you want. And then you have this external component, which is split and separated from the rest of the system, so that if the Linux kernel gets compromised and someone attacks it, you don't lose any information that is stored in the external component. And the fourth paper basically describes how such a setup increases security of the system and how you can apply this to a real scenario. So they use it for an online banking demo, where you input the crucial security relevant data for online banking in a separate window which was running outside Windows, and they hook themselves into the web browser and the SSL library inside Windows to figure out when such an interaction was necessary and make sure that the Linux kernel did never see the secret information that was stored. Well, this concludes my talk. Thank you all for attending. I hope you have fun with your exams and enjoy the rest of your summer school.
Thank you very much.